So, we were discussing current transformers in the last class, and what we actually said was that if we are having a wire like this through which I want to measure actually what is the value of current, and because it's a very, very large value, I might like to put a transformer around it, but the transformer has only a secondary winding, and the wire through which I want to measure the current itself will be taken as the primary winding, right? So, I am going to have turns around this, somewhat like this. So, I have huge number of turns wound around this, and then if I look at the current that is flowing through this, if I say that this is say 1000 amperes, and I am going to have this as turn 1, whereas this is 1000 turns, then I am going to have the current that is coming out here as 1 ampere. Right? If I assume that the current ratio is maintained properly. But at the same time, by chance if I had just connected that to a fairly larger resistance, what will happen actually is the voltage ratio will also be maintained. So, if I say this is 1000 ampere and 1 kilovolt or something like that, what I get here will be 1000 kilovolt. If I am keeping this on open circuit, because I am going to have V1 by V2 equal to N1 by N2 equal to I2 by I1. This is the normal relationship in a transformer. And if I am keeping this voltage coil, the secondary coil, as an open circuit, then I will have the voltage ratio also being followed. Or even if I connect a fairly larger resistance, I am going to have essentially the voltage ratio being followed. If the voltage ratio is followed, what will happen is, from here V1 is 1 kilovolt, so V2 will become 1000 kilovolt. But what I was meaning to do with the current transformer is only to measure the current. I don't want really this large voltage to come up. I am not interested in that large voltage at all. And not only that, that large voltage that is coming up will rupture the insulation if I have really not designed the secondary corresponding to larger voltage, which I will not. Normally I will not design the secondary of a current transformer corresponding to a larger voltage at all, because it is meant only for measuring the current, stepping down the current and measuring the current. So, that is essentially going to cause rupturing of the insulation. To avoid that, I necessarily need to either short circuit the secondary or connect a very, very small resistance. The small resistance will work actually as a short circuit. It will make it work like a short circuit. That is actually going to make, the voltage, what appears across this resistance will be whatever is my I, that is 1 ampere, multiplied by whatever is the R value here. So, what I am getting out of this will be 1 multiplied by R volts. So, if I measure this voltage, divide that by the known resistance, I will get exactly whatever is the current value. So, current transformer allows me to measure the current by stepping down the current. In the process, voltage will be stepped up if I keep it as an open circuit. So, I cannot keep the current transformer in open circuit condition at any stage. Never ever keep the current transformer in open circuit condition. Similarly, never ever short circuit a potential transformer. Both these are literally rules you guys have to follow whenever you are using CT or PT. Yes.
In the secondary coil, the voltage will be 1000 kilovolt, and if we apply like
1000 kilovolt, yeah.
And the current is 1 ampere, but if we have a low resistance.
Low resistance is as good as short circuit. I am going to have literally 1 ohm or 0.1 ohm or whatever. Low resistance again is compared to the base impedance. You will compare it with the base impedance, and compared to base impedance it should be 1000th or 1/10,000th or something like that. So, it is as good as a short circuit. See, the thing is that you are really not allowing the transformer to follow the voltage ratio at all. Just like how I told you that in potential transformer this is invalid, in current transformer this is invalid. Because I am going to short circuit it, V2 becomes 0. Because V2 becomes 0, it doesn't make any sense further. So you are going to have basically V1 by V2 absolutely not valid in the case of a current transformer. So I would say, just to reiterate, we had talked about open circuit test and short circuit test of a transformer. Under open circuit test condition of a transformer, only V1 by V2 equal to N1 by N2 is valid. No question of I1 by I2 because I2 is 0. Same way, short circuit test condition of a transformer, V2 is 0, because of which N1 by N2 equal to I2 by I1 is only valid. That cannot be equated to V1 by V2. That is not valid because V2 is 0. Right? Only thing normally we face as a problem in current transformer and potential transformers are the linearity may not be maintained, especially when you come to very, very low values of current and low values of voltages in current transformer and potential transformer respectively. Because of hysteresis, because of saturation phenomena. Very high values you may encounter saturation, very low values you may encounter hysteresis phenomena. So there will be some amount of retention of the magnetic field, because of which even when you are applying very, very minimal current, you may get a much smaller current or much larger current depending upon you are going in the same direction or coming back in the opposite direction. So you may not get exact linearity in current transformer and potential transformer when you talk about extremely larger values or extremely smaller values. Extremely larger values you may encounter saturation, extremely smaller values you may see hysteresis. So in both the cases you may find that the transformer is not working in the linear range. Got it? But in general these CTs and PTs are very, very commonly used in power system measurement and instrumentation, where thousands of amperes of current are normally passed and thousands of kilovolts of voltage are encountered, especially when you are transmitting a very large capacity of power. We may go as high as 765 kV, 400 kV and so on. So in those cases measurements really become difficult unless you have potential transformer and current transformer. Got it? So much so I am not even venturing into three-phase now. Okay? Two topics are mainly pending in transformers now. One is three-phase transformer. One more finally I would like to do, if time permits, is parallel operation of transformer. That is, if I have some capacity increased suddenly, let us say we are talking about LHC itself. So two topics are pending. One is parallel operation of transformer, the other one is three-phase transformer. Yes? When the frequency increases, why would the size of the transformer decrease? Right? That's the question. So if I say I am comparing 220 volts 50 hertz transformer, of course 220/110 or something, let me say. Another one is 220 by 110, say 5 kilohertz. I am going to compare the sizes of these two transformers. In both the cases, I am going to have E equal to 4.445 F into number of turns. Right? Now if I look at the flux in the first case, phi corresponding to 50 hertz will be 220 divided by 50, 4.44 and number of turns. Let me call this as N1. So this is going to be N1. Whereas phi corresponding to 5 kilohertz will be 220 divided by 5000 multiplied by 4.44 multiplied by N1. So clearly when I increase the frequency, flux required decreases, because d phi by dt is the one which decides how much is the voltage induced. So dt will shrink when I look at higher frequency. So I can go for less and less amount of flux as I increase the frequency further and further, which means flux density multiplied by cross sectional area, that's what gives me the flux. So cross sectional area can be decreased if I assume that I am using the same material whose flux density is fixed. B max is fixed for any material. So if I am using a particular material, then I can say for 5 kilohertz I can definitely choose smaller cross sectional area. So I should be able to say, in this case, if I say B multiplied by A1, this will be B multiplied by A2. So A2 is going to be much smaller as compared to A1. So if the cross sectional area decreases, automatically the core size will decrease. I can assume that the core size will also decrease. That's one reason why if you look at the electronic systems, generators, all those things in aircrafts, they will all be operating at 400 hertz generally. They will not be operating at 50 hertz. We are not transmitting it anywhere. It is within the aircraft itself. So we may have generator, we may have electronic systems, all of them are going to work normally at much higher frequency so that they are miniaturized. And space is at a premium in aircraft and all. So you want to reduce the size as much as possible when you are going to aerospace electronic systems. So all of them are going to work at higher frequencies, not at 50 hertz. Right? Fine? So shall we work out this 8th problem? So this particular problem statement goes as follows. The maximum efficiency of a 150 kVA 3300 by 500 volts 50 hertz single phase transformer is 97% and occurs at 3/4 of full load at unity power factor. So 3/4 of full load, first of all I can say as 3/4 times 150 kVA. This is 3/4 of full load, and unity power factor means 1 is the power factor. So this is going to be kVA multiplied by whatever load condition multiplied by power factor. This is what we have got. Okay? And this is the output. This is the output because we are being talked about 3/4 of load condition. That's what we are talking about. So that is going to be the output. So this is my output kilowatt. So input will be, so 150 multiplied by 0.75 is how much? Can any one of you tell me? I remember that as some 112.5 or something. That's what I remember from what I calculated. So it is 112.5 divided by 0.97. This is the efficiency. So this will be the input power. Whatever is the output divided by efficiency will give me the input power. Now once I get the input power and output power, I can say losses will be equal to input minus output. Right? So I should be able to calculate what are the losses. Now under maximum efficiency condition, right? Under maximum efficiency condition, P iron equal to P copper. So this will be actually losses by 2, because total losses are only considered to be iron losses and copper losses. If they are equal, I should have the total losses whatever occurs at maximum efficiency condition divide by 2 will give me the actual losses of iron and copper. But please note, this copper loss is at 0.75 times rated load. Right? Because we already said the maximum efficiency occurs at 75% of rated load. Right? So what I have got here, I should say P iron is a constant, not a problem. But P copper at rated load will be whatever I am getting here. Let me call this as PCU1 or something like that. So PCU1 divided by 0.75 whole square. Because copper losses at any load condition X is X square multiplied by copper losses at rated condition. So I am just using the same expression. Right? So now I have got what is rated copper loss. I have got what is rated iron loss. Right? What is being asked next? If the impedance is 10%, calculate the regulation at full load for power factor 0.8 lagging. What I have got is rated copper loss. If I have got rated copper loss, what we wrote just some time ago for per unit measurement, I should say P copper rated divided by 150 kVA will actually give me percentage R equivalent. Am I right? Because this is essentially I times R equivalent divided by V rated. That is what is percentage R equivalent. I am multiplying the numerator by I and denominator also by I, rated current. Then I should be able to get at the denominator whatever is the rated kVA of the system, which is 150 kVA. And at the top what I would get is I rated square R equivalent, which is rated copper loss itself. Am I right? So this is going to be actually percentage R equivalent. And what is given is percentage Z equivalent is 10. So once I get this, I should say 10 square minus percentage R equivalent square. Of course, I have to multiply this by 100. If I want everything in percentage, I have to multiply by 100, of course. So this will give me what is percentage X equivalent. Right? Please note that this is I rated R equivalent divided by V rated. Maybe I have taken everything from the primary side. This will be similarly I rated multiplied by X equivalent divided by V rated. Right? So now, if I want regulation, I can write the expression as I rated R equivalent cos phi L plus I rated X equivalent sin phi L divided by V rated, of course multiplied by 100. Now I can say that this I rated R equivalent by V rated is percentage R equivalent. I have got that directly. So I can write directly percentage R equivalent multiplied by cos phi L plus percentage X equivalent multiplied by sin phi L equal to percentage voltage regulation. That's it. Right? Is this clear? So this is based on per unit or percentage expression of the impedances, resistances, reactances, and so on and so forth. Right? Any questions on this? See, if I am taking I rated from the primary side, I better take V rated also from the primary side. If I take I rated from the secondary side, I better take V rated also from the secondary side. But when we express it as a percentage, it does not matter. Because if I am taking I rated and V rated from the secondary side, I would have taken R equivalent also from the secondary side. So it will essentially I rated multiplied by R equivalent divided by V rated on the secondary side will be very much equal to I rated multiplied by R equivalent dash, if you may call it, as what is calculated from the primary side, divided by V rated on the primary side itself. So percentage calculation, if you do from either side, it will essentially cancel out with each other. Because the moment you write V rated by I rated, it gives you Z base, either from the primary side or from the secondary side. And when you calculate the percentage R equivalent, you will always calculate it with reference to the Z base. So if you are talking about high voltage side, you are going to have the Z base itself to be larger. And if you are talking about the low voltage side, Z base itself will be smaller. So ultimately when you calculate the percentage, everything will come out to be the same. No problem. Right? Okay? Yeah. Is it coming out to be extremely different? Do you guys have the calculator so that we can try to work it out and then check? Or if you have done it, can we just take a look? His question is about 6th problem in the tutorial sheet. He says, when we actually drew the phasor diagram, if you may recall, for the transformer, we wrote, let's say this is V2 or V2 dash, if I am talking about it from the primary side. And let's say this is my current. This is the power factor angle. So let me write this as I2 dash. And this is the load power factor angle. Right? And if we are saying this is going to be I2 dash R equivalent, and I am going to have this as I2 dash X equivalent. Right? Now the total what we are getting is something like this. This is what is V1. So V1 minus V2 dash divided by either V1 rated or V2 dash rated, either way is fine, is the regulation. And when we actually calculated, we said we can neglect this vertical portion. That's how we got the expression as I2 dash R equivalent cos phi L plus X equivalent sin phi L divided by V1 rated. This is approximately the regulation. So what he is trying to say is, if we neglect that vertical component, whatever I have shown, this particular vertical component, if we neglect, then we are getting the regulation value to be different. Right? Definitely if you don't neglect that vertical component, it will be more accurate. But most of the times it happens to be, negligible. Maybe in this case it so happens that it is not negligible. Right? So either way, if you calculate it, you should be given due weightage. That's all I am trying to say. So don't bother too much about the answer as long as you know that the methodology is right. And when we neglect something or when we approximate something, we look at the practical conditions, but most of the time the values given in the problems may not be all that practical. That is also there. So sometimes that can actually give rise to some difficulty. Right? I hope so that you guys understand why leading power factor actually gives you increase in the voltage rather than reduction in the voltage. Please try to draw the phasor diagram corresponding to leading power factor condition, or if we quickly draw the phasor diagram for leading power factor condition, maybe this is my V2 dash. If it is leading power factor, I am probably going to have a current like this. This is the load power factor angle. So I am going to have I2 R equivalent somewhere here, and maybe I2 dash X equivalent somewhere here. So what I am going to get is something like this. This is what is going to be my final value of V1. And you can see that V1 and V2 dash are almost of comparable length. In fact, if you had had X to be more inwards, then actually your V1 would have been smaller in all probability than even V2 dash, which means the applied voltage happens to be smaller or slightly less as compared to what you get on the secondary side. If it is a 1:1 transformer, I am talking about 1:1 transformer. So you can say that capacitive voltage, capacitive loads normally increase the voltage that comes out on the secondary side. This happens because inherently what is there within the transformer is inductive in nature. So the capacitance kind of nullifies it. What is inherently the impedance of transformer happens to be inductive in nature, right? And there are conditions for voltage regulation where maximum regulation occurs and where minimum regulation occurs. You can try to derive those as well. That is when you write I2 R equivalent cos phi L plus I2 X equivalent sin phi L divided by V2 is regulation, right? So you can say at what point dVr divided by d phi L equal to 0. You can try deriving this, and this will be able to give you clearly at what point voltage regulation is minimum and at what point voltage regulation is maximum. Okay? Fine? All day efficiency is done only for so this is calculated only for distribution transformer. See, if it is a power transformer, I told you that power transformer normally is loaded to 100% all the time, because the generator will generate full power or it will not be commissioned at all. That's how it will be. So if it is generating full power, then the transformer will also be handling full power. So the generator transformer or power transformer will be designed in such a way that it will always have maximum efficiency at 100% load. Whereas distribution transformer will always have variable load. Because it has a variable load, it's very, very difficult to say, you know, like at what point you have to design it for maximum efficiency. So that's the reason why you generally, when you want to install a distribution transformer, you tend to look at the load profile in that area, in the distribution area. And if the load profile says out of 24 hours in a day, for 12 hours it is going to work at 65% load. Then you would try to get a transformer which will have maximum efficiency at 65% load. That's how you would generally, ask for a transformer when you go and purchase a transformer for being installed in a distribution system. So, this all day efficiency for a distribution transformer is calculated as energy efficiency. So, it is essentially energy output in a 24-hour day divided by energy input in a 24-hour day. This is the all day efficiency, normal. So, if we say that the transformer is going to be on 100% load for 4 hours with unity power factor, maybe it is going to be on 80% load for 10 hours at 0.8 power factor lag, and for rest of the times it is going to be on no load, for example. So, we have got only 8 plus 4, 12 hours, and then another 12 hours it is on no load, which is actually a criminal waste. But if it happens that way, you are going to essentially calculate what is the kilowatt output for every duration or every time interval given. You have to calculate. During that time itself, you have to calculate kilowatt output plus iron losses, which will be a constant, plus whatever is the copper loss corresponding to that load. That also you have to calculate for every duration. So, this will give you the input. So, this will be the input for every duration. Very clearly, this has to be multiplied by x square if x is the fraction of the load. Similarly, the output has to be always multiplied with the power factor if it is anything other than unity power factor. So, if I am given for 5 hours, it is working in 0.8 power factor lag with 100% load. Then I have to multiply whatever is the capacity of the transformer, that is 100% multiplied by 0.8. So, this will actually give me what are all the total inputs, and here it will give me total output. But for everything I should say output 1 multiplied by duration 1 in hours. So, I will get kilowatt hour. Then similarly output 2 multiplied by duration 2 and so on. This will be the total output kilowatt hour. That will be the total output kilowatt hour, right? So, I will have to have total output kilowatt hour divided by total input kilowatt hour. This is what is all day efficiency, right? Yeah. Yeah. Come on again. If
output loss will be different in the two cases. Like if we have two coils in an auto transformer.
yeah, auto transformer that is made from 2-winding transformer, right? That's what you are talking about. But both the windings are rated for the same KVA, clearly. Now you are going to connect them in, say, series addition. Okay? So if I am connecting them in series addition like this, and then I am trying to get the output maybe from only both of them or whatever, both of them together. So you want to apply the voltage only here, but you want to take the output from here and here. This is the output, whereas this is the input. This is what you are talking about, right? So, come on again.
Then there could be two cases, like if I apply input at that side and output at that side.
Yeah.
There could be two cases and there could be two possible values of output power.
Yeah, but you are given a situation clearly. When you are trying to calculate, you are calculating for a given situation. So if I try to say that it is a 2000 by 200 volts transformer and I am applying 2000 volts in the input and I am trying to derive 2200 volts at the output. At this condition, what I calculate as kVA would be different from if I am applying 2200 volts as input and I am trying to derive 2000 volts as output. It will not be the same. It will be different. So you should be given a situation to derive the kVA rating. Under that given situation you have to derive. So it will not be a unique answer arbitrarily. For a given situation you will get one particular answer. See, we are essentially trying to make sure that the winding current should not exceed the rated value. That's all. The care has to be taken to make sure that you don't exceed rated current value. That's it. Nothing more than that. A 20 kVA?
200 upon 500 volt, 50 hertz.
200 by 500 volts, 50 hertz.
Single phase transformer is connected as an auto transformer.
Okay.
Supply a load requiring 700 volts.
Okay.
Determine the kVA rating for this configuration. And winding currents.
kVA rating and winding currents. As a variac. Okay, so this question apparently has been given as one of the exercise questions for you guys. So this is on auto transformer. It says a 20 kVA 200 by 500 volts 50 hertz single phase transformer requires a 700 volts output from a 500 volts input. It may be, or 200 volts input. This has to be given. If it is not given, then you are going to have difficulty. Okay. It should be given clearly whether you are deriving it out of 500 volts input or 200 volts input. One of them has to be given for sure. So let us probably go ahead and assume that it is 500 volts input. So I have 200 volts, then this is 500 volts, and what we are giving is a 500 volts input. Right? And what we are having as the secondary side is, this is 200 volts, this is 500 volts, so what we have got is 700 volts. Fine? Now 20 kVA is given as 20 kVA is given as the rating of the transformer. How much is the current on this side? It will be 100 amperes. So this has to be 100 amperes. Without overloading the transformer, you would be able to get 100 amperes. Right? And now the total thing what I am getting is 700 multiplied by 100 is the total kVA of the load. Right? So, how much is it? 70,000? kVA. So, from which we should be able to calculate what is the current here. Okay, so this is 70 into 10 power 3 divided by 500, right? 14, how much? 14 5s are 70. 140? 1400 or 140? 140. So this is going to be 140 amperes. So if this is 140, that means this also has to be 140. This is 100 ampere. So this has to be 40 ampere. So hopefully it is matching with whatever is the kVA rating, even in the primary side, right? So you should be given clearly what is the kind of source that you are, adhering to. That has to be given. If that is not given, then it can't be worked out. I had taken this from one of the books, and then there are some problems that are there in Nptel. I had seen there are very good problems on auto transformer in Nptel. Nptel course has one section completely on auto transformer. There is one from IIT Madras, there is one from IIT Kharagpur also. And it's pretty good. The problems are pretty good. So you might like to take a look at those also. Because auto transformers, there are not too many problems available in many books. So in that sense, it may be of, some value if you try to take a look. Any other question?